Ever get that feeling that what we call real might be a lot weirder, maybe more interconnected than we usually think?
Yeah. Like reality isn't quite as solid as it seems.
Exactly. Like you look at your phone, feels solid, right? But what if that's just, a temporary thing in this huge cosmic dance?
Well, over a century ago, Einstein kind of threw a wrench in our usual ideas about space and time.
Oh, totally. He basically said space and time are more like Play-Doh than granite. Suddenly you've got these mind-bending ideas popping up.
Black holes, for starters,
Yeah.
which aren't really holes, but more like extreme gravity
Yeah,
zones.
cosmic vacuum cleaners with a point of no return. And then there's time travel, at least theoretically.
And gravitational waves of the universe actually wiggling.
It's wild. And the crazy part is, even now, physicists are still trying to fit Einstein's big picture stuff with the quantum world, the really tiny scale.
It's a huge puzzle.
Okay, so let's try and unpack some of this. Welcome to the deep dive. Today we're diving headfirst, pun intended, into relativity.
We want to pull out some of the core ideas, the really fascinating bits, and maybe touch on the mysteries that are still out there.
Right, without making your brain feel like it's gone through a black hole itself. We've looked at everything from Einstein's original papers to, the latest cutting edge research.
So the really revolutionary thing about Einstein, especially with special relativity back in 1905, was this idea about the speed of light.
Uh-huh. The cosmic speed limit?
Exactly. It's constant for everyone, no matter how fast you're moving towards or away from the light source.
Which sounds simple, but it messes everything else up, doesn't it?
It really does. It forces space and time themselves to be flexible. Before Einstein, everyone thought space was just space, and time just ticked along uniformly.
But if the speed of light has to be constant,
Then something else has to give. Imagine chasing a beam of light in a super fast rocket. You'd still measure that light moving away from you at the speed of light.
not slower like you'd expect.
Nope. Same speed as someone just sitting on Earth watching it.
Okay, my brain hurts already. So that leads to things like space squishing, Lorentz contraction.
That's right. If a spaceship zooms past you at, say, 99% of the speed of light, it would literally appear shorter to you along its direction of motion.
Shorter, like physically compressed.
From your perspective, yes. To the people inside, everything seems normal. But to you, the stationary observer, space itself contracts for that moving object.
Wow. Okay. And time does weird stuff too, right? Time dilation.
Yes, time stretching. Time actually passes slower for moving objects compared to stationary ones.
Slower. How much slower?
It depends on the speed, but it's a real effect. Think about GPS satellites.
Okay, yeah, I use GPS all the time.
Well, those satellites are orbiting Earth really fast because of that speed and also because they're further out from Earth's gravity. Well, that's a general relativity effect we'll get to. Their onboard clocks actually tick slightly faster than clocks down here.
Faster. Wait, I thought you said slower for moving things.
Ugh, good point. Special relativity says faster clocks run slower, but general relativity adds that weaker gravity also makes clocks run faster. For GPS, the gravity effect is actually stronger than the speed effect. The point is, time runs differently up there.
Okay, so the rate of time is different.
Exactly. It's only by milliseconds per day, but if engineers didn't account for this time dilation, your GPS location would drift off by miles within hours.
Seriously. So relativistic effects are built into finding the nearest coffee shop.
Pretty much. It's not just abstract theory, it's practical technology.
That's amazing. And what about things happening at the same time? Is that relative too?
It is. That's the relativity of simultaneity. Two events that seem simultaneous to you might happen at different times for someone moving relative to you.
So there's no universal now?
Not in the way we intuitively think. Einstein had that great quote about time existing so that everything doesn't happen at once. It suggests our perception of now is frame dependent.
Okay, so that's special relativity, constant speed, weird effects on space and time, for constant motion. But then he added gravity into the mix, right? General relativity.
Yes, 10 years later, in 1915. And this was arguably even more profound. He realized gravity isn't a force pulling things across space,
Uh-huh.
but rather it's the shape of space-time itself being curved by mass and energy.
Right, the classic bowling ball on a rubber sheet analogy.
Exactly. The mass tells space-time how to curve, and the curved space-time tells mass how to move. John Wheeler summed it up perfectly. Space-time tells matter how to move. Matter tells space-time how to curve.
So planets orbit the sun not because of a pull, but because they're following the curves in space-time created by the sun's mass, like rolling a marble around the dip made by the bowling ball.
Precisely. It's a geometric theory of gravity, and it made some incredible
Like
predictions.
the bending of starlight.
Yes, famously confirmed by Arthur Eddington during the 1919 solar eclipse. They saw stars near the sun appear shifted because their light was bent by the sun's warped space-time, just as Einstein predicted.
That must have been a huge moment.
It was. And there have been many confirmations since. The way Mercury orbits, frame dragging, and just a few years ago, in 2016, the direct detection of gravitational waves
Those ripples in space-time itself.
caused by massive events like black holes colliding billions of light years away. Feeling those tiny ripples here on Earth was a monumental confirmation of general relativity.
Okay, you mentioned black holes. Let's go there. These are predicted by general relativity.
They are regions where space-time is curved so extremely by gravity that nothing, not even light, can escape once it crosses a boundary.
The event horizon. Sounds ominous.
It is the point of no return. But even black holes got weirder thanks to Stephen Hawking.
Right, Hawking radiation. He said black holes aren't perfectly black.
He proposed that due to quantum effects right near the event horizon, black holes should actually emit a very faint thermal radiation. It suggests they slowly evaporate over immense timescales.
So they glow faintly and eventually disappear.
Yeah.
That's bizarre.
It is, and trying to understand what happens right at that horizon, combining quantum mechanics and gravity, leads to paradoxes.
Like the firewall paradox. Sounds dramatic.
It's a deep puzzle. Quantum mechanics insists information can't be destroyed, but general relativity suggests anything falling in is lost forever. The firewall idea is one problematic potential outcome if you try to force the theories together, suggesting a high energy barrier at the horizon.
That sounds like it breaks general relativity.
It potentially does, and it highlights this fundamental clash between our theory of the large general relativity and our theory of the small quantum mechanics.
They just don't play nicely together, especially in extreme places like black holes or the Big Bang.
Exactly. General relativity describes a smooth, continuous space-time. Quantum mechanics deals with discrete units, probabilities, fuzziness. They speak different languages at a fundamental level.
Which is why physicists are searching for a theory of everything, or quantum gravity.
Precisely. A theory that can unify gravity with the other forces under a single quantum framework. That's the ultimate goal for many theoretical physicists.
And the main contenders are still string theory and loop quantum gravity.
Those are the two most prominent approaches, yes. Very different ideas.
String theory says everything is made of tiny vibrating strings, right?
In essence, different vibrations correspond to different particles, including the graviton, the hypothetical quantum particle of gravity. It requires extra spatial dimensions, which is a complication.
Yeah, just a few extra dimensions. And loop quantum gravity.
That takes a different path. It suggests space-time itself isn't smooth, but is quantized, made of incredibly tiny discrete chunks or loops at the Planck scale.
So space and time aren't fundamental, but emerge from something deeper.
That's one of the mind-bending possibilities some of these theories suggest, that our familiar smooth reality is like an emergent property, like wetness emerging from H2O molecules.
It's just incredible to think about. Now, going back, Einstein's ideas weren't instantly accepted, were they? Even he had doubts about some things, like quantum mechanics.
That's true. He famously disliked the probabilistic nature of quantum theory, saying God does not play dice. And relativity itself faced significant opposition initially.
Who was resisting it and why?
There were physicists like Ernst Gurr and groups like the so-called Academy of Nations. Part of it was reluctance to abandon absolute time and the ether, these long-held classical concepts.
The ether, that invisible stuff light was supposed to travel through.
Right, relativity did away with it. Plus, the mathematics was complex, abstract. Some felt it was becoming detached from physical intuition, more like mathematical philosophy than physics.
So it was a radical shift that took time to digest.
Very much so. But the experimental evidence just kept mounting. General relativity, in particular, has passed every test thrown at it with flying colors.
Which is amazing, but it still doesn't explain everything, does it? We've got these huge mysteries like dark matter and dark energy.
Absolutely. These are perhaps the biggest puzzles in cosmology today. General relativity works incredibly well for the matter and energy we can see, but most of the universe seems to be made of something else.
Dark matter, the invisible stuff holding galaxies together.
Yes, we see its gravitational effects, but we can't detect it directly. It seems to outweigh normal matter by about 5 to 1. What is it? We have candidates, WIMPs, axions, maybe tiny black holes, but no definitive answer yet.
And dark energy, that's even weirder, isn't it? Making the universe expand faster and faster.
It is. It seems to be some kind of energy inherent in space itself, pushing everything apart at an accelerating rate. It makes up almost 70% of the energy density of the universe.
Wow. So most of the universe is stuff we don't understand.
That's the current picture. Is it a cosmological constant, as Einstein once proposed and then discarded? Is it something else entirely, like dark magnetism or back reaction? We don't know.
Are we likely to find out soon? What are
Yeah.
the next steps?
Well, new experiments and telescopes are coming online. Missions like Euclid will map the universe's expansion history and structure with incredible precision. The ELISA mission aims to detect gravitational waves from space, opening a new window. These could give us crucial clues about both dark energy and dark matter.
So better observations might point the way. And what about the really sci-fi ideas, like wormholes? Does relativity allow for those?
Theoretically, yes. General relativity contains solutions that look like tunnels through spacetime, connecting distant points or maybe even different universes.
But can they actually exist? Could we travel through one?
That's highly speculative. Most simple wormhole solutions require something called exotic matter, with negative energy or negative pressure to keep them stable and open. We've never seen anything like that.
So probably not happening anytime soon.
Probably not based on standard general relativity alone, but perhaps within a full theory of quantum gravity, the rules might change. It's an area where theoretical physics bumps right up against science fiction.
It really shows how much Einstein changed things, but also how many questions are still left. He gave us this incredible framework.
That revolutionized our view of the cosmos, absolutely. Space and time aren't just a static background, they're dynamic players in the universe's story.
But there are still these huge gaps, these fundamental mysteries about gravity, quantum mechanics, and the basic constituents of the universe.
And that's what makes physics so exciting. His work continues to inspire and challenge scientists today, pushing us towards an even deeper understanding.
So as you go about your day, just think about that. The solid ground beneath your feet. It's part of this constantly flexing stage of space-time. Reality might be subtly shaped by unseen dark matter, pushed apart by dark energy, and echoing with gravitational waves from long ago.
Makes you wonder what other things we take for granted might be far stranger than they appear.
Absolutely. If this deep dive got you thinking, definitely explore these ideas further. There's a whole universe of mind-bending physics out there waiting.